Hello, everyone. All right. Good morning, class. I'm going to go ahead and get started. Um, just an FYI, my internet has been really weird since we've come back from vacation. So um, if my stream stops or if you can't understand me or something like that, please type it into the chat and I will have us switch over to the Zoom room. Okay. All right, so I will go ahead and get started. Um, all right. Yeah, it is choppy. I apologize. Um, it's really frustrating because I didn't change anything, but class, I'm gonna be right back. Okay, I have to stop the stream to change the settings. So, all right, I'm back. So let's try this again. Okay, so what we're going to talk about today, there are two types of waves that occur in nature, okay? And so what I want you to think about is a slinky, okay? There's a slinky. And imagine that I'm trying to make a wave go along the slinky, okay? There's actually two types of waves that I can create. I can take the slinky and I can push the end of it in, and I can pull the end of it out. So I can kind of take the slinky and I can jiggle it this way. All right. And if I do that, what's going to happen is the slinky will have places where it's stretched out, and then places where it's squeezed together, and then places where it's stretched out, and places where it's squeezed together, like that. Okay? And so these are the waves that are traveling down the slinky. Okay? So this type of wave is called a longitudinal wave. Okay? And for a longitudinal wave, the medium vibrates parallel to the direction of wave travel. Okay, so I can see that to make the wave, what I had to do was I had to vibrate the slinky left-right, and then the wave itself goes left and right. Okay, so that's what I mean by parallel. So a good example of a longitudinal wave is a sound wave. Sound is a longitudinal wave. Longitudinal waves have locations where the medium is squished together, and these locations are called compressions. And then they have areas where the medium is stretched out, and these are called rarefactions. Okay? So that's called a longitudinal wave. We could imagine taking that slinky, and instead of vibrating the slinky left-right, we could vibrate the slinky up and down. And if we did that, we would create a slinky wave that kind of looks like this. Okay? So we can see that the medium is going up and down. So this type of wave is called a transverse wave. Okay? So for a transverse wave, the medium vibrates perpendicular to the direction of wave travel. Okay, so the difference is parallel versus perpendicular. Transverse waves have peaks and valleys. So the peaks are called crests, and the valleys are called troughs. So we have crests and troughs, compressions, and rarefactions. The best example of a transverse wave is light. Okay, electromagnetic waves. All right. So some mediums can have both longitudinal and transverse waves. Okay, so for example, a slinky can have longitudinal waves and it can have transverse waves traveling through it. Okay, some mediums can only have one type of wave or the other. For example, the air only allows longitudinal waves. So you can only have sound that is a longitudinal wave. You can't have transverse sound. It's always going to be longitudinal. Similarly, light waves are always transverse waves. Okay? But if we think about a slinky, it can have both. If we think about the Earth's crust, you can have both transverse and longitudinal waves. So it depends on the medium. All right? All right. So for your so we're going to focus on a particular type of transverse wave today, which is an electromagnetic wave. All right. There's a question. What does that say next to compression? Right here. I'll rewrite that. Rarefaction. So an electromagnetic wave is basically the type of wave that light is. Okay, what we perceive as visible light is one type of electromagnetic wave. Okay. So electromagnetic waves, they travel at the speed of light. Okay. The speed of light is so common in physics that it has its own symbol. Its symbol is c. And the speed of light is 3 times 10 to the 8th meters per second. So nothing can travel faster than the speed of light. That's the highest speed that we can have in the universe, as far as we know. So different electromagnetic waves are classified by their wavelength. Okay? And so this creates what is called the electromagnetic spectrum. So part of that spectrum is visible light. So there's visible light. There's what is called ultraviolet light. There's what is called X-rays. There's what is called gamma rays. Okay. There's what is called infrared. There's what is called microwave. And there's what is called radio waves. So these are the parts of the electromagnetic spectrum: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. So I'm sure you've heard of probably infrared. You've probably heard of microwave. You've probably heard of radio. Actually, you've probably heard of all of these. Okay. These are all the same type of wave. They are all electromagnetic waves, but they have different wavelengths. Okay. So what is the wavelength of the lambda value of each of these parts of the electromagnetic spectrum? Well, for visible light, the wavelength is approximately 10 to the minus 6 meters. Okay. For infrared, the wavelength is approximately 10 to the minus 3 meters. For microwave, it's approximately 10 to the minus 2 meters. For radio waves, it's approximately 1 meter. Okay, so you don't have to memorize these, but the idea is that as we go from right to left, the wavelength gets bigger and bigger. Okay, ultraviolet, the wavelength is about 10 to the minus 8 meters. X-ray is about 10 to the minus 10, and gamma ray is about 10 to the minus 15 meters. Okay, so gamma rays have the shortest wavelength of all the electromagnetic waves, but it's the same type of wave as the wave that your eyes are seeing. Okay, the only thing that differentiates radio waves from visible light is wavelength. Okay, now because of the difference in wavelength, there's a difference with how these waves interact with matter. Okay, so for example, X-rays, because of their short wavelengths, they're good at passing through matter. Okay, so that's why we have X-ray images. They can pass through matter unless it's dense matter, like bone. So we can see the bones inside someone's body with X-rays. Radio waves, they pass really well through the atmosphere. They can go a long way through the atmosphere, so we can use radio waves. So anyways, there's a lot of different, so you should, memorize the names of these. But the point is that visible light, what we think of as visible light, is just a small, small part of the full electromagnetic spectrum. Interesting point. The sun emits mostly visible light. Okay? So if we think about evolution, why can we see visible light? It's because our eyes have evolved to be the most sensitive to the type of light that our star is producing. Okay? You can imagine a world where the star is cooler and it's emitting mostly infrared light. Our eyes would have evolved differently to be most sensitive to infrared light. Okay. So if we think about, I want to talk more about transverse waves. So transverse waves can vibrate in two different ways. Okay, so a good example of that is, okay, if I pluck a guitar string, I could take the string and I could pull it up and then release it. So that means I'm creating a vibration that goes like this. Or I could pull it out towards you guys and release it, in which case it's vibrating like this. So those are two different transverse waves. All right. So if I have a string, for example, the string could vibrate up and down, or it could vibrate into the page and out of the page, like this. And those are both perpendicular to the direction of wave travel. Okay. So these two different ways transverse waves can vibrate. Are called polarizations. Okay, so you could have, let's say there's a wave coming at you. The wave coming at you could be vibrating up and down, or it could be vibrating side to side, like this. All right. So those are called the polarizations of light. It could be coming at you like this, or it could be coming at you like this. Or it could be coming at you sort of like diagonally, but diagonal is a superposition of up and down and side to side. Okay, so it's not really anything new. Some sources of light are polarized. Some are what we would call unpolarized. So to be polarized means that all of the waves that are being emitted have the same polarization. So that all the waves that are coming out are up down, or all the waves that are coming out are polarized side to side. Okay. So this means that all the waves have the same orientation. All right. To be unpolarized means that you have equal amounts of each polarization. Okay, so for example, the sun is emitting unpolarized light. So the sun is emitting as many waves that are going up and down as there are side to side. All right, so there's equal amounts of each. So we would say it's unpolarized. There's not any preference for one type of polarization. All right. It is possible to have what is called a polarizing filter. A polarizing filter only allows one type of polarization to pass through. Okay, so I like to think about a polarizing filter sort of like a window. Okay, so here's your polarizing filter. Okay, and it's kind of like the bars on a prison window. So if you think about this prison window has vertical bars, so you could stick your hand out the window and move your hand up and down, but you couldn't move it side to side because it would bump into the bars. Okay, so that's basically what a polarizing filter is. So for example, if you have a polarizing filter, okay, and going into that filter is both up and down polarized waves and side to side polarized waves. I'm drawing this from kind of a 3D perspective. And that is going into the polarizing filter. Then the ones that are going side to side are going to get blocked. And the only thing that's going to come out is the up and down polarization. All right. So they're removing all of the waves that are polarized the wrong way. So then we could think about what would happen if we then passed this wave through a second polarizing filter that is rotated to only allow side to side. In that case, nothing is going to come out. nothing is going to come out. Because the only wave that came out after the first polarizing filter was up and down polarized, and then after that it's side to side. This one is only going to allow side to side, so nothing's going to come through. All right? So a general rule of thumb is that if unpolarized light hits a polarizing filter, the intensity, so I want you to take a guess. Type it into the chat. What do you think is going to happen to the intensity of the wave? Okay, if you think about this, unpolarized light, so it has an equal amount of up, down, and side to side. It hits a polarizing filter. So what percentage of the waves are going to be removed? So what do you think that's going to do to the intensity? Type it in the chat if you have a guess. It is going to decrease, but can you say how it's going to decrease? Yeah. So the intensity is going to get cut in half. Okay. So that's important. If unpolarized light hits a polarizing filter, the intensity will be cut in half. And furthermore, the outgoing light will now be polarized. Okay, because going into this polarizing filter, we had both up, down, and side to side, and now after the wave comes out, we only have up and down. So now it's polarized up and down. So it's going to be polarized just like the filter. All right. So we're going to do a couple examples. So 111 part 2. So there's a rule. So let's imagine a front view of a polarizing filter. Okay, so here's a polarizing filter like this. Okay, and we're looking straight at it. So it's an up-down polarizing filter. All right. And then there's a wave that is going into the filter. All right. Let's suppose that the wave is polarized at an angle. So here's the angle of the filter, and here's the angle of polarization of the wave that is entering the polarizing filter. Okay, so there's some angle between them, which we'll call theta. There is a law called Malices Law, and what it says is that the intensity of the outgoing light is equal to the intensity of the incoming light times the cosine squared of that angle. Okay? So basically it tells you how much of the wave is blocked if it is polarized at an angle. Okay? So that's called Malice's Law. And of course, so the outgoing wave is going to have a smaller size, and it's going to be polarized in the same direction as the filter. Okay, so it's going to be up-down polarized, and it's going to be smaller. So this might be the input, and this might be the output. All right, so let's do an example with Malice's Law, just to show how it works. So let's suppose you have unpolarized light. So unpolarized light has an equal amount of up, down, and side to side. And it hits an up and down polarized filter. Okay. And then it's fed into a polarizing filter that has an angle of 20 degrees. So this angle that it's rotated is 20 degrees. All right. And then it's passed through another polarizing filter that makes an angle of 90 degrees. Like that. And so we want to know, what is the intensity that goes out? Okay? And let's suppose that the incoming intensity is, let's say, 800 watts per meter squared. All right, so type it into the chat. What's going to be the intensity of these waves that after they go out of the first filter? So you have unpolarized light of intensity 800 watts per meter squared. What's going to be the intensity after it passes through that first filter? Uh, 50% of that, so that's going to be 400. Excellent. So we got 400 here. Okay, 400 watts per meter squared here. Now that 400 watts per meter squared is going to get fed into this polarizing filter. So now I'm going to use Malice's Law. Okay. So Malice's Law tells me that the outgoing intensity is going to be equal to the incoming intensity. So the incoming is not 800 because it's already passed through this first filter. So we have 400 times cosine squared. Now this light that comes out of this first filter is going to be polarized up and down. Okay, so this filter is 20 degrees angle to that. So we have cosine squared of 20 degrees equals that gives us an intensity of 353 watts per meter squared. Okay. So the intensity is reduced. And furthermore, the outgoing wave is going to have that angle of 20 degrees. So it's going to be polarized at 20 degrees. All right. So now to find the final output, I'm going to use Malice's Law again. Okay. But I'm going to use this input intensity. so 353, times cosine squared of, now here's the tricky part. This filter is rotated 90 degrees to up and down, okay? But if we look at the output of this second filter, the output is going to be angled at 20 degrees. So what is the angle? So this angle in Malices Law is the difference in angle between the polarizing filter and the wave itself, okay? So this wave is angled at 20 degrees, and the polarizing filter is at 90 degrees. So that means that the angle between them is 70 degrees, okay? So I do 353 times cosine of 70 squared, and I get that the final outgoing intensity is 41 watts per meter squared. So that's the answer. Okay? So that's my lesson for today, and I will see you in the Zoom room.